are about what these computers, or these models of computation, models of computers can't do. So we, in the end, prove, actually somewhere in the middle of the class, prove that there are problems that computers cannot solve. So, how can you make such a deduction? You have to, first of all, formalize what you mean by a computer. It has to be very precisely stated. And then how do you go through the mathematical argument and the deduction that people did in the 1930s and 40s, even before computers, to realize that there are things that computers can't do, and actually come up with a mathematical proof of them. And then later in the course and later in the progression of the theory of computation, people try to make that a little more practical and ask the question, okay, for things that computers can do, can they do them quickly? Or are there some problems which, yes, they're certainly solvable by computer, but never solvable efficiently? And we'll get into that as well. That theory is not as completely closed and finished as the theory that says there are things that computers can't do at all. And so that's what this class is about. And along the way, there are some practical things that you learn, particularly in the beginning, on finite state machines, which I'm talking about today. But for the most part, this is a theoretical course about what the human mind can deduce about the nature of computation, and it's pretty amazing. So, of course, the tools we use here are abstract reasoning and mathematical reasoning, proofs by construction, contradiction, induction. And so you should be comfortable with all of those kinds of tools. And recursive thinking is very important in this kind of material. Being comfortable with recursion, recursive descriptions. The ability to draw is helpful. Draw little diagrams. That's about it in terms of the background. You should have had CS20 certainly. If you had 122, that's helpful, but it isn't a requirement. Math 108. Is it still a course that they teach? Does anybody know 108? Yeah, okay. The last time I taught this was 12 years ago, and Math 108 was the course that it's on the math component and abstract, sort of introduction to abstract math and proofs. So that kind of a class is helpful, but again, it's not an absolute prerequisite. All right, so everybody feel you've got the right background, and how many people have taken 122? Okay, so about half the people. It isn't a requirement at all, but it is certainly, it's in the same, it's the class that's as close, it's the closest to this one in terms of theoretical skills, but it's a more practical course. But everybody's had 20 or some kind of discrete math or proof-oriented type of course. Okay, so any questions about the hand-waving stuff? I always feel like the first lecture is to the instructors is the most important, where I'm telling you the big picture of the philosophy and all that. It's always the most boring to students because you don't really know what I'm talking about because you haven't seen the specifics yet. And it's really a lecture I should give at the end after you've seen all the material and know what I'm talking about. But there's never time at the end, so we do it this way. But any questions at this point? Okay, so I'm starting with chapter 1 in the book. Chapter 0 is just sort of really elementary mathematical things. It tells you what a function is, what a proof by induction is. And if you have any weakness in that, you should review it or review some other sources. So we're going to start with finite state machines. Machines, and this is also sometimes called finite state automata, however you spell it. Anyway, whatever. Finite state automata, and we just have to dive in. So these concern strings over an alphabet that are processed by this machine called the finite state machine, and then either accepted or rejected. All right, so we have to have an alphabet, and that's usually abstractly, that alphabet is just usually abstractly written as sigma, and let's just look at a particular one, 0, 1. So this is the binary alphabet. So we're looking at strings that are written over zeros and ones, so binary strings. Okay, and then a string is just a concatenation of characters from sigma. Okay, so this is sigma in English, but since all of this stuff, most of this stuff came from Europe, and the various Muslims said this was sigma. Okay, so if you really want to get into the mindset of this field, this is sigma. Okay, anyway, you have a concatenation of characters from your alphabet. So, for example, 0, 0, 1, 0, 1, 0, 1, that's a string. Okay? And we have abstract symbols for that. For example, W might be used to write that, to refer to that, or X, that's the mysterious variable X that we were speaking of earlier. So X is a string, or W is a string, in this particular case, it happens to be that one. And then we have machines that or a machine that accepts or rejects a particular string. So let me just put up one. Goes like this. So or 1. works, these things are called states. Q1, Q2, Q3. States in this case. Feeding W into this machine. And you start out in state, in this example, we start out in state Q1, and then depending on what you see in W, you follow the arrows. Okay? So if you were to see, let's just take the example of W equals 0, 0, 1, 1, 0, 1. Okay? So you just follow the arrows based on what you're seeing in the string. So the machine, this is a machine, this is a finite state machine, M, is processing the string W. So we start out in Q1, that's the start state. You first see a 0, which means you follow the arrow that's labeled 0, and you're back to Q1. And you see another 0, and you're again back to Q1. Then you see a 1, and you're in Q2. But even though this is a final state, you haven't finished processing the string. Okay? So you're in the final state, but you haven't finished processing the string. That's important to note. Then you see another 1, so you're back in Q2. Then you see a 0, you go over to Q3, and then you see a 1, and you follow, this says if you see a 0 or a 1, you follow that arrow back to Q2. And now, you're in the final state, and you've finished processing the string. And so in this case, M, the machine, accepts the string W. It accepted the string W because it finished processing W while it was in, and ended up in a final state or an accept state. Okay. Now, what would happen if we use the following string? Okay. Then we do the same. Where would we end up? What state do we end up in this case? In Q3. In Q3 is not a final state or an accept state. So in this case, the machine doesn't accept the string. In this case, the machine rejects the string. Okay. Rejects the string. Okay. So it's pretty simple. If this is your finite state machine, or somebody shows you a particular finite state machine like this, and then you're given a particular string, you just follow the yellow brick road here until you finish processing the string. And if you're in an accept state or final state, then that machine has accepted the string, otherwise it's rejected the string. Okay. Anybody got any questions? There's one very natural one it should have. Well, the question I was thinking somebody might have is, well, what if you're in a state and there happen to be two edges out with the same label? Okay? I mean, in this machine when I first load up, there was only one edge that had a 1, one arrow that had a 1. What if you have two arrows that have a 1? So you're in this state, and the next character is a 1. Where do you go? You go this way or that way? Well, initially, we're not going to have that. Initially, we're talking about deterministic finite state machine, which means that whatever state we're in and whatever symbol we see will always be, whatever character we see in the string, will be an unambiguous way to go, a deterministic way to go. There won't be any choices or questions. Later we will talk about, maybe in the next lecture, probably next lecture, we'll talk about finite state machines that do have choices. But at the moment, there are no choices at all. So the computation is completely deterministic. Right? All right. So any questions about this example or some of the terminology that's been introduced? Or okay, so let me make this a little bit more formal. When we talk about a deterministic finite state machine, we describe it with a number of pieces of information. Q is a set of states that the machine has. I'll give it M, or M. Okay. Sigma, of course, is the alphabet used for the strings. Okay, so we need to specify both of those. And then you need a transition function. Okay, this is a transition function. That means if you're in a particular state and you see a particular character, what state do you next go to? Okay, so this is a function. What does it take as, I call it input, but it's a fancier mathematical term. What's the fancy mathematical term for what a function operates on? The parameter argument, or the set of arguments is called the Domain? Yeah, I think it's domain. Okay, so how do we describe the domain in the case of the finite state machine? Again, what the transition function is supposed to tell you is, based on what state you're in and what symbol you see, where's your next state? What was your next state? So what are the elements of the domain? The alphabet, well, yeah, I guess you can say that, right, because that's a symbol, right? Yeah, right, if you want to put it very mathematical, I'll write that down that way. Q cross sigma. Okay, this is what's called the Cartesian product. That means all combinations between the set Q, that's a set of states, Q is a set, and the set of characters in the alphabet. All possible combinations, all possible pairs. So this is saying a particular state and a particular character in the alphabet, and that describes the domain of this function, delta. And then the range is what? How do you describe the range of the function? The function takes a state and a character and produces what? A state, yeah. So it is a function from state cross character to state. And this is what we drew up here pictorially, schematically. If you're in state Q1 and you see a 1, then you go to Q2. Okay, this is the transition function, delta. If you're in Q1 and you see a 0, you go to Q1. That's another way of drawing out the transition function. A more, different way, a less pictorial way, is just with a table. Q1, Q2, Q3, Q2, Q2, Q2. Q3 and 0, 1 goes to Q2. Yeah. Okay, so that's describing the transition function delta. Okay, so this is abstractly what a transition function is. This is a particular transition function that's associated with this finite state machine. Okay. So what this is saying is, whenever you want to describe a particular finite state machine, you have to describe a transition function, and the transition function is a particular instantiation of this. You know, what is the, as we'll say, this is the delta part. It's taking pairs of states and characters and telling you what state each one of those goes to. Okay. And then what else do we need? We need Q1 with the start state. You have to specify what the start state is, and you have to specify the set of final states. Okay. So anytime somebody specifies all of these things, you have a complete description of a finite state machine. It's not necessarily deterministic. Whether or not it's deterministic, actually this is, because there's only one, this maps is just a single state. Okay. So this is a description of a deterministic finite state machine. This is the abstract specification of what it means. And anytime anybody tells you what a set Q is, what sigma is, what delta is, what Q1 is, what F is, then you have a complete description of a particular finite state machine. And you should be able to go from this description to one of these drawings. Okay. Or the other way around, you should be able to go from one of these drawings to one of these descriptions. And I'm not sure if the first homework asks you to do that explicitly, but you should be able to do that. Okay, so let's just look at a few more examples. Oh, one more thing. When you look at a finite state machine, you can describe it this way, you can describe it this way, and in a sense, as input to a computer, that's a full specification. That's but for humans, there is usually a more concise kind of way of describing what this particular finite state machine is, or what is the set of strings that finite state machine accepts. Okay? So if you just look at this for a while and you think about it, what is the set of strings that this finite state machine accepts?
That's not quite right. There's not 1, 0, 1, 0, 0. It's a separate screen, but it has 2 zeros.
Okay, you're saying 1, 0, 1. Okay, well, this ends in an even number of zeros. Okay, so the ending part does have an even number of zeros here. The total number of zeros is odd, you're right, but the ending part just has an even number. Yeah.
What about 0, 0, 0, 1?
0, 0, 0, 1. Yes, well, that ends in an even number of zeros. 0 is an even number of zeros. Okay, that's what I was saying earlier was sort of the tricky part. Yeah. Okay, so I think this is right, but you have to remind yourself, remember that 0 is an even number. So if it ends in 1, that's ending in an even number of zeros. So it has to have a 1, because in order to get over to this final state at all, it has to have a 1. And then as you're going around here, well, when you come through here, if you use a 1, you can stop, and then you're ending with a 0 number of zeros. Or you go again, and if you come back to 0 with a 0, since you had to go that way with a 0, if you stop at that point, then you have an even number of zeros. So whenever you stop, it's either because you just went through that way, so you end with a 1, or you went through this way with a 1. In most of the cases, you're ending with an even number of zeros. Or you finish with this 0. But you had to get there with that 0, so that's an even number of zeros too. Okay? Yeah, I've asked you to go along there several times. It's not just 2 zeros, it could be 4 zeros and so on. You can make a nice proof, a more formal proof, that this is the right description of, please stop it. 10 to 12, yeah, okay, fine. I thought people were getting nervous. I thought it was like we should be finishing at 10 after or something. No, we've got a long time to go. All right, so if you wanted to actually prove that this is the correct description of what this machine, of the set of strings this machine accepts, what kind of technique would you use, by the way? What seems like a natural proof technique for this? Yeah. Proof by contradiction. Okay, I'm sure you can make a proof by contradiction, and maybe I should make that like a homework problem. But there's another one that I was thinking of. Well, I only mentioned a couple of proof techniques here. Okay, that's contradiction too. Contrapositive. This one begins with I. Induction, right. And we would probably induct on the length of the string. Okay, you want to say that this is a description of the set of strings that this machine accepts. Well, what are all the strings of length 1 that the machine accepts? Just one in this case. It's just the string that contains a single 1, and that's satisfied that this contains a 1 and ends with an even number of zeros. Okay, and then you say, well, suppose this is true for strings of certain length, now longer length, and so on. So I think you could get an induction proof based on the length of the strings. Okay. All right, let's just do another example. We're trying to get really, really familiar with. Oh, actually, but I want to introduce one more expression. So shoe. A topological operation. So generally, if we just have a set of strings, that's called a language. Okay, so the formal definition of what a language is in this topic area is just some set of strings. Okay? And then for a deterministic finite state machine M, the set of strings that M accepts is called language. M accepts, and it's usually written as L of M. Okay? So this triple here means defined as, instead of like a mathematical equality, which would be for, if we use 2 of these. When you have 3, it's just saying this is a definition. So if we have a finite state machine M, we can talk about L of M, that's the language that's defined by finite state machine M, or it's the language that M accepts. Okay. So let's look at another finite state machine and see if we can figure out what the language that is that it accepts. Okay. 1, 0, 1, 2, 1, 0. Okay, so we start out, our start state is also our final state, and well, it is what it is. Let's look at some strings that it accepts. If it goes, well, it accepts 0 as a string, definitely, because you can go in there. It also accepts the empty string. Empty string is usually written by this little epsilon. Okay, that's the empty string. It accepts the empty string because the start state and the final state are the same. But to put it more correctly, the start state is a final state. Okay? So that's the empty string. What about 0, 1, 1, 1, 1, 0? Accept or reject? Yeah, it accepts that one. 0, 1, what about that one? It rejects that one, yeah, okay. So now can we psychoanalyze this machine and say more concisely what is the language that it accepts? What? Empty string or ends in 0. Okay, so yes, it certainly accepts the empty string, and the only way to get into the final state here, other than starting the final state, is with a 0. Okay, so that seems right. So we always want to go in 2 different directions. One is to say that in your description, everything you say that accepts it actually does accept that, and that anything that's excluded by what you describe is not accepted. Okay, so everything you said, it's either the empty string or it's a string that ends in 0, and definitely we can see that that's necessary. That it be the empty string or ends in 0, because this is the only way to get to the final state. And if it ends in something other than a 0, that's all the set of the other ones, then where are you? The only way to end in something else is to get a 1 either this way or 1 that way, in which case you're in Q2, which is not a final state. So that sort of, in a hand-waving way, is an actual proof that what you said is right. So ML is either the empty string or a string